Okay, so coming back to our vectorial representation of the Berger vectors. So, let us say that this is our original Berger vector and it splits into partials. So, this one is edge, remember that part, and now when we have this partials B1 and B2. So, the component and here the line vector is like this. So, remember the line vector is like this for the original vector. So, the line vector is like this and we are assuming that this is also the line vector for the B1 B2, and in this particular part there will be transition phase, but over here looking at it U remains same. So, when we come to the resolving the partial Berger vectors along the x and y axis, what it means is that B1 x is actually nothing but a edge dislocation. So, this is E. B2 x is similarly edge dislocation, and B1 y and B2 y are actually screw dislocations. Okay. Now, what do we see here? That there is a pair of oppositely signed screw dislocations, and if we assume something like this where the distance between them is d, then we can find out, or we can write a equation for what should be the forces between these screw dislocations. For oppositely signed dislocations, whether it is edge or screw, we know it is attractive. So, we can give a negative sign to it. So, it will become minus GBS. I will write S for screw. We will find out, or we will write in what exactly this will boil down to in a moment. GBS squared by 4 pi d, and there is also force between the edge dislocation. Now, these are in the same direction. So, there is edge dislocation here, there is edge dislocation here, distance between them is d, and this will be repulsive in nature. So, the sign will remain positive and there will be a 1 by nu in the denominator. So, the Berger vector I have written as E. So, this is but now what is this Bs and Be? So, whatever we had here as B1 or B2, which is of the form B1 is of the same type as B2 is of the same form as A by 6 112, and the angle here we know is 30 degree, that you can find out directly from geometry. So, now the Berger vector for the edge dislocation would be cos 30 of this. So, let us say let us call this as B1. So, this is becomes B1 cos 30. So, the B edge is equal to B1 cos 30. Similarly, the Berger vector for the screw dislocation would become B2 sin 30. Now, when we put this over here, you can, I will leave this exercise to you, that what will be the net force, will it be attractive or repulsive, and as you would see that it would actually come out to be net force is repulsive, meaning that this partial will repel this partial. So, they will want to move away from each other. So, the two partials are like this, and because of the repulsion they will want to move away from each other. But what happens when they move away from each other? So, this is important information that we have here, that Fe plus Fs, this net force is repulsive, which implies that two partials move apart. Now, it is the two partials which are moving apart, and if you look at it in terms of the extra half plane, what it would look like is something like this, which is not a very good scenario in terms of energy and a little difficult to draw at the same time. So, let me, okay, so I will have to first draw what we already had earlier. So, if the dislocation was perfect, this is how it would be, and in the alternate planes we had like this, and now, but these are the two extra half planes that form part of the partials, and they will want to repel each other. So, they are repelling each other, and what you will get is something like this. As I said, it is not very easy to draw. So, I am just trying out here to draw this, and then I will be able to explain to you. So, now what do we have here? Okay, so I have already made a mistake here. Okay, so here this was your extra half plane, which is dark green colored, this is extra half plane light green colored. So, this is a perfect crystal, but now these two want to move apart. So, extra green plane comes over here, the lighter green plane comes over here, but the bottom side of it were still in the same place, because only the top parts are moving, and because of that what you will get called as the stacking fault. You remember now let me remind you again that this is, what is this plane? This plane is of the type 111, and 111 have ABC kind of packing. So, in this particular case, when your partials just move apart, then it displaces and it forms the atoms, nearest neighbor atoms, and what you will get. So, in this particular case, if they, let us say it was something like C A B C A B. So, this is a ABC sequence that should have been there, but now after this what will happen for the region in between these. So, we are only talking about region in between these, because beyond this it is still perfect crystal, but in between this region what will happen is C A B. Now, over here C should have come, but now it will be the A type of plane. So, now there is a repulsion, there would be energy, extra energy, because now these two atoms are sitting one very close to each other, which is not their low energy configuration, and because of that the energy in this particular region increases. So, now it will be beyond this, only at this particular layer there is a stacking fault. So, this is the stacking fault which I have represented over here. So, this plane is same as this plane. So, this is the stacking fault. And in other words, what you have is a partial dislocation like this, which is of the type in by 6 112, and there is this width d, and then again another partial dislocation A by 6 112. So, this whole system, this is called a extended dislocation. So, this whole thing is called the extended dislocation, and it will act for most of the cases, it will act like one unit. So, if you apply stress, it will move simultaneously and so on. But more important aspect is that now we have a stacking fault energy over here, which means that there will be some energy associated to the region wherever this stacking fault has been created. So, if the thickness is d, and the energy would be, so energy would be proportional to D, while F net would be inversely proportional to D, meaning it will become smaller and smaller as D becomes larger, and therefore, there will be a equilibrium spacing of partials. What I am trying to say is that the width of the extended dislocation would be dependent on material properties. And it is not very difficult to show that this width would actually be proportional to Gb square by 4 pi gamma. And what is gamma here? This is the stacking fault energy. And to be precise, let me again draw where is this D. So, this is one partial, this is another partial, there is stacking fault, and this whole thing is wide D, the width of this is D, which is what we are calling as the extended dislocation. So, this D will be proportional to Gb square by 4 pi nu. Now, so we have we see that based on the Berger vector, the stacking fault energy, there is a fixed D. Now, what you can observe experimentally is D. So, and you already would know G and B. It would also mean that you can find out what will be the gamma, that is the stacking fault energy of the material, and people have indeed calculated or not calculated based on this equation. Actually, they have back calculated the energy, and they have found that for aluminum the spacing is, so let me put it in a clean table. So, this is the spacing, this is the gamma, and this is the material. So, for aluminum people have observed that width is A. Smaller width would mean that gamma is very large, and it does indeed come out to be 140 millijoule per meter square, which is high, as you would see compared to other materials. Copper width is 5A, much thicker, and therefore, the energy is smaller. So, smaller energy means the dislocation partials are able to move apart much further away, and silver is even smaller, smaller in the sense energy, which would mean larger width. So, we get 7A, and this is the stacking fault energy that people talk about when with respect to FCC, which is also related to the twin boundary formation, and this has also to do with the partial dislocations. Now that we have discussed the partial dislocations, I will pose one question to you. This particular extended dislocation was formed using a edge dislocation. So, we assumed that this is the Berger vector, sorry. So, we assume that this is the Berger vector, this is the line vector, and similarly here, not similarly here, here this is mixed character. Yeah, now that is another important aspect that you should realize, that the partials are always mixed character, because or by default they are mixed character, because as you can see the line is lying at 30 degree. So, if it is parallel to the original U, it will have a mixed character, it will have both edge and screw character. That is what we saw when we resolved B cos 30 and B sin 30. So, this is what we solved, assuming that this is a edge dislocation. Now, you have to go back and see if I were using originally a screw dislocation. So, Berger vector is like this, the line vector is like this, and therefore, this would be a little bit different. So, B1 and B2, these will still remain, if as long as it is parallel to you, they will still remain mixed character. Of course, the real partial dislocations, now that I am talking about it, let me draw it. So, this is the one that we solved. The question is whether you will get net repulsive force when you are talking about as dislocation with parallel, that is screw character. So, this is now screw, and over here you can assume these are your, and the in most general case, like I said, partials will be mixed character. Okay. Now, what I mean is that you can also have line going like this, and since the Berger vector is like this, somewhere over here it may still be parallel, somewhere it may still be perpendicular. So, there will, just like in our regular dislocation, there may be certain points which are pure edge and pure screw. So, here it is pure screw and so on. So, here also this will be pure screw, but in general it will have a mixed character. However, what you have to go back and look is see whether the net force comes out repulsive or attractive. Okay. So, now few things before about this extended dislocation before we move on to understand more about the partial dislocations. Sorry, before we start to move about finding out ways to describe dislocation in a FCC system. So, when a stress is applied, dislocations move together, the extended dislocations move together. The leading partials, now there are two dislocations over here. So, if you apply, one of them is the leading partial, other is the trailing partial. So, the leading partial creates stacking fault and trailing partial removes it. Okay. So, these are some important aspects when we are talking about the partials. Now, there are several possible type of dislocation, and do all of them in the FCC dissociate into partials? What are the Berger vector for this? How do we know about this? And for that, again we will have to go back to our FCC unit cell. So, here if you connect these atoms which are the phase center over here with the one over here like this, what you get is a tetrahedron, and you would be able to see that the edges here are 1 1 0 and the planes here are 1 1 1, and this is called Thomson's tetrahedron. So, there is a model which has been made out using this Thomson tetrahedron, which very nicely explains all this edges and direction. So, now I will show you the model. So, this is the model that I was talking about. In the diagram that I showed you, that it is a tetrahedral, and you can see this is a tetrahedral, it has 4 faces, and each of the edges of this tetrahedral, now if you go back in the diagram and then compare it with this, you would realize that it represents one of the 110 direction. In fact, it covers all the possible 110 direction and all the possible 111 planes. So, these are all the different 111 planes that are possible in the FCC system. These are all the different 110 direction that are possible in the in the FCC system. So, what do we see? We have 1, 2, 3 and 4 different 111 planes, and of course, the negative of it. So, if you ignore the negative, there are only 4 distinct 111 planes. And how many 110 directions we have? We have 1, 2, 3, 4, 5 and 6 different directions, 110 directions for a FCC system. This is not all. We get a lot more information from this Thomson tetrahedron. Now, I will focus on one particular plane. So, now you look over here, this is one particular 111 plane, and I will rotate it so that the 111 that you see is in the right orientation. So, now this is representing 111 plane. What do we see? We see that any of the 111 plane, in this particular case it is actually the 111, you get 3 different 110 direction, and these 110 directions, again we are just taking in not taking the negative. If you take the negative, then there will be the other side. So, but in direction, these are the 3 possible 110 directions. So, it means that this particular plane can have Berger vector like this, Berger vector like this, Berger vector like this. And if we are talking about pure edge dislocation, so a Berger vector with this will have line vector like this, a Berger vector with dislocation with this Berger vector, edge dislocation would have line vector like this, dislocation with Berger vector like this will have a line vector with like this. So, it is also giving us the possible direction for the edge, pure edge dislocation. Similarly, the screw dislocation, which have to be parallel to the Berger vectors. So, the screw dislocations will be oriented either like this or like this. Now, what else do we see from this? Even before I go to the partials, which is also information that you can obtain from this Thomson tetrahedron. Another thing that I want you to observe is that now let us look at, this is one type of 111 plane, and now let's look at another type of 111 plane, another not type, but another member of the family 111 plane. So, this is bar 1 and 1. So, what do we see? That these 2 planes have one common edge, and this common edge represents the common Berger vector in the 2 planes. So, this is another important information that we get, that whenever there are 2 planes, there will be one common Berger vector, other Berger vectors are not common. So, this particular plane can have dislocations with bar 1 0 bar 1 and 0 1 1 1, which is not common to this one. So, in other words, it would mean that if you have a dislocation with Berger vector, in this particular case which the common one is 1 bar 1 0, then a dislocation with Berger vector 1 bar 1 0 can collide in bar 1 1 plane or in 1 1 1 plane. So, there can be a cross slip of dislocation, and when we talk about cross slip, it has to be screw, you just keep that in mind. So, a screw dislocation with this particular Berger vector can cross slip only onto this, and you remember we solved one example where we showed that the P1, that there was a dislocation moving from P1 to P2 to P3, and when we said that P1 and P3 have to be same, there cannot be any other possibility. So, there is these are the only 2 planes, and therefore, if it moves from here over here, then it can only move back to this one, because the Berger vector does not change. So, this particular dislocation with a constant Berger vector can only move in either of these 2 planes. So, that is another important aspect that we see from the Thomson tetrahedron. Next, what else do we see? We see that there are 4 different planes, and all the 4 planes are connected to the other plane at least by one common direction. So, it would mean that it would mean two things. One, that every dislocation will be able to, every dislocation in FCC, if it is a screw dislocation, will be able to cross slip. Another, that it will be able to cross slip only onto two different planes, it cannot have any third option. And next, that all the planes would be connected with each other. They can be connected in the sense that here we have one common Berger vector for each. So, if you see 1 1 1 and 1 bar 1, this is the common one. If you look at 1 1 1 and 1 bar 1 1, then you see that this is the common one. If you look at this one and this one, then this is the common one. Similarly, for other planes we will have some common directions. So, these are the information that we are able to obtain for full dislocation. Now, let us look at what else information do we get about the partial dislocations. So, yes, Thompson tetrahedron is powerful, that it gives you also information about partial dislocations. So, let us say this is now a full dislocation Berger vector. Now, these two directions that you see over here, these two directions which are almost at 30 degrees, not almost, it is exactly at 30 degrees, they are the Berger vectors of the partial dislocation for the dislocation that is gliding on this plane. So, remember, although this particular direction is common in two planes, but if it is gliding in this particular plane, then it can get only these two Berger vectors as partials. So, for this bar 1 1 0 Berger vector of full dislocation, it can dissociate into bar 1 2 bar 1, and this is in this direction. So, we will have to take the other direction, which will become bar 2 1 1. So, that will be the two partial Berger vectors, and you see that your calculations or the mathematics of FCC becomes so easy using this Thompson tetrahedron. You do not have to apply your brain, whether it is I mean, you should apply your brain, but you do not have to do the calculation every now and then to find the dot product and find whether it is coming out to be 0 or not. So, all those information are inherent over here. Now, still one more aspect that we see over here is that these Berger vectors, they are not on the edges. Okay, the partial Berger vectors, they are not on the edges, they are inside the plane. What does that mean? It means that these partial dislocations cannot cross slip. Even if they are screw dislocation, they will be confined to only this particular plane. It cannot move on from this one to this one. So, if you are, let us say if this happens to be the line vector of the partial dislocation, so it will become a screw dislocation, but unfortunately for it, this is the only plane onto which it can glide. It cannot glide onto the other plane. So, these are some very important aspects that you are able to get from it. You are able to get the full Berger vectors, you are able to get the partial Berger vectors, you are able to get the planes on which the dislocations can move, and you are also able to find where they will cross slip. There are more utility to this, and we will come back to this when we talk about it in the next lecture.